Hi there. Just before Christmas, Tektronix in Element 14 sent me an MDO3000 series oscilloscope so that I can use it for my tutorials and videos on the Element 14 forums and other tutorials that I do on my blog. As part of the set of tutorials I want to do with this, one of the first things I thought I would show you is how to use the I2C serial decoder that's built into it. The reason I want to do this first is because I actually have a need right now to diagnose some problems that I've had on the I2C bus talking to some LCD displays for the power supply project. I didn't include that in the power supply project because I needed to just focus on that particular video. But I want to now go back and have a look at some of the things that can get you, first of all, in setting up the scope to work with the I2C bus, and secondly, to show you using the scope some of the issues with, for instance, an Arduino, which is what I'm using in this case, and having even short pieces of wire going to a I2C to 8-bit expander chip, and how even over a short range they can actually have problems with the signal quality if you don't terminate them properly. So anyway, I'll not go into it too much more detail than that and get right to the practical demonstration. So let's go and have a look at the oscilloscope setup first for I2C and cover a couple of the issues that you may come across there if you're not too careful. And we'll have a look at the waveforms that are coming out of the Arduino for our example of how to use the oscilloscope. So this is the MDO3000. The specific model that I have is an MDO3054. It's a 500 megahertz mixed domain oscilloscope, and what Tektronix sent to me with it in collaboration with Element 14 was the serial decoder software, which is for I2C and SPI bus, and also the power software for checking out switch mode power supply efficiencies and things like that, which we'll go into in a later video. In this particular situation that I'm doing, I have an Arduino UNO hooked up through the I2C bus, which is using ports A4 and A5, which are often used for analog inputs on the Arduino, and I've hooked it up to a 2-line by 16 character LCD display using an 8254 I2C to 8-bit port expander. This is a fairly typical way of hooking up an LCD display to the Arduino where you're wanting to use a lot of the ports for other things, because if you hook the LCD display up directly, it really doesn't leave you much for other activities or I/O devices. So anyway, when I first hooked this up, I actually ended up with a problem where the software seemed to be perfectly correct, but absolutely nothing would be coming up on the LCD display. So let me just go down to the Arduino a minute and show you exactly what's happening. And here it is here. And if I just zoom in there a little bit, you can see that on this LCD here, I've got the oscilloscopes hooked up on the back to the I2C ports. But if I just press the reset button on this Arduino, all right, you can see it's just come back on now. Absolutely nothing is happening on the LCD display. There is a very faint first line of characters that are the squares for them, at least, are illuminated slightly, but there's no backlight, nothing happening on this LCD display. And as you can see, I've only got a few inches of actual cable hooked up to this right here, right? There's 2 for the power and 2 for the I2C. Maybe they're 8 inches in total, nothing else, and it's just not working. All right, now I can show you other situations with one of my other LCD displays where a similar hookup does work. So what that really tells me is whatever's going wrong is probably very marginal. So everybody, I think, that's watching this knows what a square wave basically looked like. You know, these microcontrollers, they talk in binary, so you either have a 1 or a 0. Even the analog outputs are actually pulse width modulation, which is a 1 or a 0, and it's just the ratio between the 1 and the 0s that allows you to simulate analog voltages. So what do we need to look for an I2C bus to be able to figure out what's going wrong here? Well, the first thing we want to do is look at the actual waveforms and see whether the oscilloscope can even see the data that's coming out of the Arduino and whether it can decode it properly. So what we have, if I just reset this for a moment to default, that way we can start afresh. We have channel 1 and 2 turned on at the moment, so here and here, and we know that we're dealing with basically 5 volt TTL logic. So I have both inputs set to 5 volts, which means 1, 2, 3, 4. I'm going to reduce these down to 2 volts per channel. That way they'll fit on the screen. And my time base is currently set to 4 microseconds per division. So you'll see right now on the screen here, occasionally the signals, about every 4 seconds, you'll see some changes in the amplitude of the signal here, right there. Now obviously this is running a bit too fast for the display, so I'm going to reduce this down to say 400 microseconds per division. That might let us see a bit more of what we're trying to evaluate. Okay, there you go. Now we need to be able to capture this, so we'll look at the trigger levels over on the oscilloscope over here and make sure that we're sitting maybe mid trigger point. And in order to look at the waveform, because this is only outputting once every 4 seconds, it's difficult to actually capture it. So we need to go into single shot mode. So if I just press the single button, and it'll capture. Now we've got a captured waveform on the screen from the I2C bus, A4 and A5, like I said. Now, one of the really nice things that we've got on this Tektronix MDO3000 scope is the ability to zoom in on the display. So just by rotating this pan and zoom dial, we can actually home in and look at a smaller part of the waveform here. And the outer area we can actually just zoom in and slide either way on the screen. Now I think you can see that fairly well, that this is a pretty crappy square wave. There's a huge RC kind of slope on the rising edge there, which I would imagine would cause problems for a lot of timing critical situations like there is in the I2C bus, because you've got a clock where the rising edge or the falling edge, depending on how it's configured, is clocking in the data. Now what I have here is that the channel 1 is my data channel and channel 2 is my clock, and you can see that if I just move channel 1 down a moment on the display here, you'll see that we have the clock regularly for the whole byte here. We have a gap between bytes being sent out, and then we have more data, more clocks regularly at regular intervals. And on the data side of things, you can see the first one is a 0, then there's a 1, and then there's lots of zeros. Okay, and then again the same for the second one. You've got the start byte, and then you're clocking in data depending on what the microcontroller is sending out. Now, in some cases, you don't necessarily see, because of the refresh interval, a fine enough display. So what I'm going to do right now is change my time base and try and do a single shot, but at a higher time base, so that we can actually have a better resolution of the signal to have a look at. So that, I think, now shows us, I've gone down to 20 microseconds per division. And if I expand out on that, you can see now quite clearly that the display is pretty. If I just slide over there to the start bit, you can see the start bit here. There's a little bit of impact on this edge, actually causing this edge to dip a little bit. You can see it's got a heavy RC time constant on here, caused by capacitance on the wires or something like that, or the fact that the output of the Arduino has not got a strong enough pull-up on it. And then even on the data line, there's some quite large slopes here. So it would be difficult for any microcontroller or expansion device to be able to actually figure out what that data is supposed to be, because there are not clean edges on it. So even though this is a very, very short piece of wire on my Arduino here, that could easily account for why things are not being displayed properly on this thing. Now, what we can also do is we can use the MDO3000 to actually decode the bus. And I've got the software already installed in here. So if I hit the B1 and tell it I want I2C, so we just go up here, I can have parallel I2C or SPI. So I'm going to pick I2C. I'm going to define my inputs as A1 is my data, so I just have to switch these around right now, and A2 is my clock. Okay, so that's that set. Now if I clear this out, here's my I2C line. So if I just do another sample now and wait for it to trigger that, it should now need a little more data so that it can have a chance of actually decoding any of this. Okay, right back almost instantly. One of the other inputs you can set up for this is the thresholds. So when I look at the thresholds that are currently set, it actually defaulted to a user setting, probably because of me playing around before. So what I've got is the clock threshold set to 0 volts. Well, of course, that's no good whatsoever, and my SDA is set to 2.8. Both of these are TTL levels, so what I really want is 5 volt CMOS setting. So there's one actually defined here already. So if I just scroll down and pick the 5 volt setting here, where it sets the actual threshold to the 2.5 volt line, and we'll give that a go. All right, I think that should probably, well, actually I don't even have to re-trigger. As you can see here, now that I've adjusted that, it's immediately come up now and decoded the data. So if I just scroll this across and do some resampling here, all right, so now we're getting data coming in. If I just shrink that down so I get more data on the screen, we can expand it up afterwards. The one nice thing about the MDO3000 is it has a very, very deep capture buffer, so you can set it up so that you can get a really long amount of data that you can't actually figure out on the screen, and then later on you can actually go in once you've captured the single sample and zoom right in on the particular area that you want. So what I'm going to do is I'm just going to adjust this oscilloscope now to capture a much deeper set of data. So the first thing I would do is go into where is it? The acquire menu, and right now I've only got 10,000 sample record length, so I'm going to change this one way down to let's just say go the whole hog and put it as 10 meg, and we'll see what that can actually do for us now. So there it is triggered. As you can see, we have a lot of data that you actually can't see right now. Now down here, B1, it actually was a little box circling around there for a second that was saying not yet computed. And what that does is it once you've captured it, the software will go in and analyze the captured waveforms and try and decode the data and put it on the screen. So if I actually run this in normal oscilloscope mode, what you'll probably find out there is that it will not manage to decode anything. If I just wait for this to finish what it's doing, because I was messing with it. All right, it's in auto trigger now, and it's going to every 4 seconds it's going to get a waveform, but because it's continually triggering, it's not going to allow it to do any decoding. All right, and it may or may not even show anything on the screen, just because it may be off the side because I'm sitting at 2 milliseconds. So it's actually, not being able to capture it. But if I run it in single mode, it will actually capture the waveform to memory, and then once it's done, it will run through and compute the I2C bus decode. There, it just came up. You can see it in here now. Now, of course, at this level, I can't see what's going on, but and if I zoom out here, that's great. All right, I can now see the decoded packets here. Okay, but it's not easy to work with this and then just use the horizontal position to scroll through things. What is a better way to do this is if you go back to your normal full screen waveform. All right, if I just recapture that. Okay, so I've got a huge amount of data here that I can look at. Just wait for it to compute it. All right, now if I use the pan and zoom control on the MDO3000, what I can do now is on the top screen, you see here, I have the waveforms that have been captured in a small window, and now I can actually scroll through the data here and actually look at an expanded view of what's coming in. And I think one of the things I'm noticing here is that everything just says 2020 20 2020, whereas I know because of the software that's not what's been put out onto the LCD display. It's going to be very different to that. So it shows that even the MDO3000 right here is having a hard time trying to decode this data that I'm putting out to the LCD the screen. So how do I fix that? Well, if you look at the I2C interface specifications, what it actually tells you is that you should have a pull-up resistor to the 5 volt rail on the I2C bus. And what I've done is I've built a small board here, and it's just a set of headers. There you go. And on the back of the board I've put 2 resistors. They're 10K pull-ups to the 5 volt rail. And I'm going to just put this in series with the circuit the data lines coming through, and we'll see if that improves this and see whether we can actually capture the data properly now. Alright, so what I've done here is that little board I just showed you, the two resistors on the back going from the 5 volts to the data and the clock line. I've just put the wires that were originally going straight to the display onto the input of that board, and then I've linked yet another wire from that board over to the LCD display. Now you'd be thinking that, you know, I've more than doubled, because this other wire is about, I don't know, 12-14 inches long. I've more than doubled the length of wire on there, and it'll probably make things worse, but in fact it's actually going to make it better. Now I haven't reset the Arduino yet, so the initialization hasn't been set to the LCD, but I haven't changed anything else except for the pull-up resistors. So let me just hit reset on the Arduino again, and you'll see that now this thing is going to burst into life. There you go. So hello world, I love Arduinos, great. This is part of the demo that came with the Arduino software, and now as you can see it is going through there quite happily, showing me the codes that should be showing up before. And the only difference I've done there is put an I2C pull-up resistor on the data and clock line. So if we go back to the oscilloscope now, and we'll see what difference the capture makes. Remember before when we were looking at this, it was not able to decode the data one little bit. So now we will give this a go. Okay, everything's hooked back in again, and I've just got my finger holding on the reset button of the Arduino, so I'm just going to let go of it now. I've basically got the same settings as I had before, so we'll see, have a look at the waveforms and see what we actually capture this time. So it's just busy computing. Alright, there's the first capture we've got, so we'll just expand that out. The first thing I want to look at, which is why I'm expanding out on the Timebase versus zooming in, is actually the shape of the signals. And you can see here now that these are much cleaner than what they were before. If I just turn the bus signal off for a second, you can see here that the edges, even though they're still rounded a bit, I've only got a 10K pull-up on each of the lines, rather than something like a 4K or something a little bit less. But you can see the rise times are much sharper. They've now got square tops on because of that, and so therefore it's much cleaner. So let's see if this will actually be able to be decoded by the I2C bus decoder on the oscilloscope now. So whereas the very first capture we've got here, you can see that it's already showing you an improvement on the captured data, and that what we had before across the board was just 20s, which I think was just an aberration of the way the data was coming out. Now we have address writing, so this actually shows us what it's doing as well, whether it's reading or writing from the I2C bus. So it's actually doing a write to address 20, and it's writing the value 80 out to the address. That's probably turning the backlight on the I2C display, because one of the bits is just dedicated for the backlight. Now if we just run this single capture again so that we can get a lot more data, I'm just going to reduce the time base down to about 2 milliseconds so we get a large amount of data captured. And we'll just run that, and we'll catch one of the refreshes, so right there. Now as you can see, there's a lot more data now being captured, and on the LCD display, of course, it's all now displaying correctly and it's going through the various character sets. But now you can see here that the I2C decode has finished doing its calculations, and now if we just zoom in on the data here, all right, we can actually now, let's just go to this first captured packet right here. You can see now that we have a 20, a 0, a 20, a 10, a 20, 20 being the address. So when you're zoomed out a little bit where it doesn't have room to display everything, see if I go out a bit further, it'll tell me that it's address write 20 and things like data 00. But if I actually shrink the display to get more on there, it'll actually drop the text and just show it with colors. So you get a little green bracket to say it's the start of the packet, and then the first byte being the address and the second byte being the data. So you can see here it's got a 20, 0, 2010, 20, 0, and then a small gap, probably because the microcontroller is doing some thinking, and then a 2001, a 2011, a 2001. Now of course we've got, that's probably just an XY addressing instruction, because if you look at the code, which I'll post the source code for this, you'll see that the first thing it does is set the cursor position, and then it outputs the data to the cursor, to that cursor position. So if I scroll now to the other packet here, you'll see that it's very, very different. So you've got the 20 for the address, and now it's saying 44, 54, 44, 43, 53, 43, 46, which it basically is the data that's being written out to the display. Now you can actually have different, I'm just wondering whether I can actually show this in ASCII. Event table maybe. Let me just check. There's various ways of looking at the data here. So this is actually now looking at it in a table view on here. If I just zoom in a little bit, you'll be able to see better what it's showing us. So we know the waveform is now working just by the addition of those two pull-ups, and the oscilloscope also is now able to read the data too as well. And what it's showing you is that through the time intervals, it's actually got the data here being shown as hex, and the address is being shown. I'm not sure if I can make it show ASCII. I haven't figured that out yet. It's got hex and binary. It doesn't have ASCII output. It would be nice if it could show the ASCII characters as well for something like this, but you know, I'm not complaining. It doesn't take much to actually go and look at what these character codes are. But anyway, you can see now that it's actually reading the I2C bus quite happily now. So using the MDO3054 with the serial bus, basically I was very quickly able to, number one, from the oscilloscope side of things, look at what the waveforms were and determine the fact that they were very, very poorly formed with the huge slopes on the edges there, on the leading edges. And secondly, I was able to determine that you know, even the oscilloscope could not decode the data. Now that the oscilloscope is decoding the data, I can see exactly what is being sent out to the display and what addresses are being used. So if I had some problem with my software, I could also verify that the codes were being sent out correctly. What I'll do in a later video is actually hook up an external A to D converter and have a much, much tighter data frame and actually correlate the binary data that's coming either on a parallel port or an ADC or DAC, and show what's happening on the I2C bus feeding into the microcontroller, so that you can see is actually the full functionality, but in a much smaller packet that's easier to read. Because this one right now that I'm using for this LCD display has probably got 100 or more bytes of data being sent out for one packet. So. Oh, if you have any questions you want to ask or other things you want me to try out with the oscilloscope, please let me know in the forums or in the on the YouTube comments area, and I'll see what I can do. If you have any questions about this particular test I was doing, any additional information about setup, then you can ask that there as well. I think one quick thing I wanted to just re-mention as well is that one of the first traps I fell into when I was first trying to use the oscilloscope for the I2C bus decoding is that I was leaving it on automatic trigger mode, so not single sample mode, where it would just capture a one shot and then decode it. And because it was running in automatic mode, it actually was not able to have the time to decode the bus and show it on the screen before the next set of data was coming in and changing it. So that's a small trap there. It really won't work very well if you're using it on automatic auto re-trigger mode. Make sure it's in single shot mode, and make sure you have the right thresholds, of course.